Hi Geometry, this is Unit 2, Lesson 8, page 247. We're going to take notes on Lesson 8 in class, but unfortunately, I'm probably going to run out of time to talk about what a converse is, which is what they discuss in the summary. So let's discuss that at this time. So first of all, we know from Unit 1, this is back in Unit 1, a long time ago, that the perpendicular bisector of a line segment is exactly those points that are the same distance from both endpoints. So if you remember, when we would construct the perpendicular bisector back in Unit 1, you guys would use your compass and you do a big circle with center A, and then you do a big circle with center B. And then where those intersected would be all the points that are equal distance from A and B at the same time. That was my perpendicular bisector. And we learned how to construct that in Lesson 1. So this first sentence is just something from that time. So what we're going to do is we're going to use the definition of a perpendicular bisector, what it is, this perpendicular bisector theorem, to learn about what a converse is. So first of all, let's look at this first sentence. This is the statement, and this is the converse. So if we look at the statement, there's an if part. If a point is on a perpendicular bisector of a segment, and then you'll find that there's a then part. Then it must be equal distance, the same distance from both endpoints of the line segment. Okay, great. We know that's true. We know that from Unit 1. So now this is a converse. A converse happens when we flip the if and then part. So instead, we're going to take the orange part and put it in the front. If a point is the same distance from both endpoints of a line segment, and now we're going to put this at the end, then it must be on the perpendicular bisector. So that's a converse because I switched the if-then parts. When you switch the if-then parts, that's when you get the converse. So in this case, it happens to be that my converse is also true. So let's go on to see what it says. These statements are converses of one another. Two statements are converses if the if-then part are swapped. The converse of a true statement isn't always true, but in this case, both statements are true. Let's look at an example of when the converse isn't true. So let's move our book down to the bottom of the page, and let's write in an example. So first of all, let's do the statement. My statement is going to be, let's say it is 102 degrees. Oh, if. I got to start with my if, sorry. If it is 102 degrees outside, then it is hot. So let's take that for a true statement. So maybe I've got somebody out there watching this that does not think 102 degrees is hot. Well, let's just pretend like everybody factually believes if it's 102 degrees outside that it is considered hot. So now let's look at the flip-flop of that. We're going to put the then part in front. So the converse is when I switch it around. So the converse, if it is hot outside, then, and this is where I'm going to swap it, I'm going to put the if part in the back. Then it is 102 degrees. Well, you can pause and think about that and realize that does not really make sense because a lot of people think 100 degrees is hot or 99 is hot or really 85 can be hot if it's sunny and no air conditioning. So if it's hot outside, then there's no reason it has to be exactly 102. So the converse of this statement is actually false. It doesn't have to be exactly 102 if it's hot outside. So that's an example of a statement and a converse where the converse is not true. And the one using the perpendicular bisector theorem, which we'll prove in class when we take our Unit 2 Lesson 8 notes, we'll write a proof for this. The converse happens to be true. So let's take a look at practice questions. I want to give you a few helpful hints here. So I'm on page 248, and I'm going to discuss numbers 1 through 5 at the moment. So on this one, number one says each statement is true. Select all the statements for which the converse is also true. So let's look at number 1, for instance. So the statement, if two angles are vertical, then they are congruent. So if you remember, when two lines intersect, the angles across from each other, I've got to move this down, sorry. When two lines intersect, the angles across from each other were congruent. Those were called vertical angles, and they were indeed congruent. So yes, if two angles are vertical, then they are congruent. Converse. Now I'm going to flip the then part and the if part. So now I'm going to say if two angles are congruent, then they are vertical. Well, that's not actually true. If they're congruent, they don't have to be vertical. So let's take a look at some examples when that's not true. For example, when I have parallel lines, my corresponding angles are congruent to each other, and these aren't vertical. When I have an isosceles triangle, my base angles are congruent, and those aren't vertical. So I've got lots of examples of when two angles are congruent, but they're not necessarily vertical angles. So that wouldn't work. Let's look at one that is true, but it confused some kids last year. So let's take a look at D. It says, in an isosceles triangle, the base angles are congruent. I just drew that up there. And yes, in an isosceles triangle, when I have two sides congruent, my base angles are also congruent. So let's flip-flop the if-then and see what we get. So the converse says, if the base angles of a triangle are congruent, these two, then the triangle is isosceles. So if the base angles are congruent, then it's isosceles, and that's true. Now last year, I had some kids say, well, maybe it's equilateral. They said, hey, you know what? It's equilateral and not isosceles, so this is false. And I love how they're thinking, because they're thinking really hard. I mean, they are thinking about this problem. But I want to talk a little bit about what it means to be equilateral for a minute. So let's pretend like you have a neighbor, the Smiths, and they're married, and Mrs. Smith is a doctor. So if you greeted her outside, you'd probably call her Dr. Smith. You say, hey, Dr. Smith, how are you today? You probably wouldn't say Mrs. Smith, even though if she's married, she could be considered Mrs. Smith. So if something has a better name, a more accurate name, you use it. So an equilateral triangle where all three sides are equal and all three angles are equal is actually considered isosceles as well. But it's more special than being isosceles because all three angles are equal. All three sides are equal. So we call it equilateral. But it really doesn't prove this statement false. If the base angles of a triangle are congruent, then the triangle is isosceles, even if it was equilateral. Technically, an equilateral triangle is isosceles, but we would never call it that because it's more important or more special than that. It's equilateral. So D would be true. So let's take a look actually at number 4. Number 4 is going to be a proof you're going to try to write. So let's set this up. This is my given right here. So let's write that out to the side as the given. Angle A is congruent to angle C, and side AE is congruent to side CE. And those are marked in my diagram already. And I'm trying to prove that angle AD, or triangle, sorry, ADE is congruent to triangle CBE. So this is actually, depending on how you write the given, this is really just a 3-line proof. If you put all the given on one line, this is a 3-line proof. So in this diagram, there's something you should mark because you know it's true. So for example, we should mark our congruent vertical angles because we know that that is true. And then I can see the angle, side, angle. This side is in between my two angles, congruent to the angle, side, angle, and the other triangle. So these two triangles are congruent by angle, side, angle. So when I write a proof, the first thing I write is the given. So I'm going to write the entire given on this line right here, and my reason is going to be the given. I then am going to mention that these two angles are congruent. So let me catch up with you and write the given. So I could name this angle going either direction. I'm going to start at A and call it AED. So angle AED is congruent to, but now over here, I have to use corresponding vertices. So A matches C. So I'm going to write CEB, angle CEB, and that is because vertical angles are congruent. And now I know my two triangles are congruent. I write what I'm supposed to prove. That always goes in the last line. Triangle ADE is congruent to triangle CBE, and that was because of angle, side, angle. Lastly, let's look at number 5. It says triangle DAC. That's the entire triangle. The whole thing is isosceles. We can see this mark here and this mark here. What information do you need to show that triangle DBA? So DBA is this little blue one right here that I just shaded in, is congruent to triangle CBA. So CBA is this little purple one right here. By the side angle side triangle theorem. Well, I'm looking at this and I noticed that the little blue triangle and the little purple triangle, they both have this side in common. That's congruent. They also share this side. So if I could put my finger on the blue and purple triangle and pull them apart, they'd come apart. So I can see my side and my side. So if I want side angle side, I need an angle in between them. So if I could get this little angle congruent up here, I'd have side angle side of one triangle congruent to side angle side of the other. So it looks like I need this little angle congruent. So I either need angle DAB congruent to, and then you guys fill in the matching angle over here. Or if I knew that AB was an angle bisector, it also would split that angle in half. So fill this in and then finish up numbers 1 through 5 for your homework. Thank you very much.